Okay, before we can get into solving some pressure and volume and temperature problems, I want to go over some basic conversions in terms of converting different pressure values. Converting temperature is pretty easy. We have a temperature in Kelvin, which is equal to the temperature, I want to write temperature here, temperature in Celsius plus 273. That's a pretty easy one. When we're dealing with pressures, it'll come a point where we'll need to convert between different units of pressure. So we need to know, and this is something you're going to need to know, that 760 torr is equal to 760 millimeters of mercury, because they are the same. It's equal to 1 atm, and it's equal to 101.3 kilopascals. And so a lot of times we'll have things like we'll have to convert 710 torr to atm. They're always one-step problems, and we're always going to use this little line of information, which is the same as when we had like 1 mole equals particles equals gram formula weight. We're going to do the same thing. So here I have 710 torr, and I want to get rid of torr, and I want to convert to atm. So I look up here and I say, okay, in front of atm it says 1, in front of torr it says 760, and then I can just go ahead and calculate by taking 710, multiplying it by 1, and then dividing by 760. And I end up with 0.934 atm. If I want to convert atm to millimeters of mercury, I'm going to do the same thing, 5.6 atm. I want to get rid of atm. I want to convert to millimeters of mercury. Again, the number in front of atm is 1. The number in front of millimeters of mercury is 760. And so I can go ahead and take my 5.6 and multiply it by 760, and I get 4,256. And as again with all sort of problems, the converting between units for pressure, this 1 atm, none of this will limit any of your significant figures. So we sort of consider it a wash, and we only ever deal with significant figures at the final answer. So I'm fine if you want to leave some of these bigger numbers in your calculations and then just take care of that significant figure situation at the end. And then we have 240 kilopascals to atm, so 240 kPa. We want to get rid of kPa. We want to go to atm. Again, we have 1 atm, and then we have 101.3 kilopascals. So I do 240 divided by 101.3, and I get 2.37 atm. So those are our conversions. Now, looking at some of our basic gas law problems, we're going to start looking at things that have a little bit longer sentences. Consider a metal container with a volume of 22.4 liters filled with a gas at 1 atm at 273 degrees Kelvin. What will be the new pressure if the temperature increases to 298 Kelvin? The tricky thing about this one is I gave you a volume, a pressure, and a temperature, and a new temperature. So what variables am I dealing with? Well, the thing is that it's a metal container. So will a metal container change volume? No, it won't change volume. And so this value is irrelevant. This is how chemistry starts to get to be a little bit harder. You need to really identify what type of problem it is and how things are getting easier and harder. So really, I have a pressure temperature problem. Okay, so I'm going to write P, T, P, T. My pressure is 1 atm. My initial temperature is 273 Kelvin. My new pressure is what I'm looking for, and my new temperature is 298 Kelvin. First thing I'm going to check is my temperature has to be in Kelvin, and it already is, so that's not something that I need to deal with. Second thing that I'm going to check is my temperature is going up, so I want my pressure to go up. So I'm going to go ahead and put that arrow there because that's going to be my check later on. Then I'm going to go ahead and do the problem, 1.00 atm. I want my pressure to go up, so I'm going to put 298 on the top. I'm going to put 273 on the bottom. And I'll go ahead and multiply 1 times 298 and then divide it by 273. And I end up with 1.09 ATM, which indeed is bigger than the 1 ATM. If I look at this problem, calculate the decrease in temperature when 2 liters is at 20 degrees Celsius is compressed to 1 liter. This one's a little more straightforward. So I have a volume and a temperature, a volume and a temperature. See how pulling these numbers out really helps with the solving of the problem? I have 2.00 liters at 20.0 degrees Celsius, and I'm going down to 1.00 liters. So Celsius, let's get rid of that, plus 273. So I have 293 Kelvin. And then again, I'm going to go ahead and look at my volume. My volume is going down, so I also would like my temperature to go down. I'm going to start with the thing that I have one of, so 293 Kelvin. I do want my temperature to go down, so I'm going to put the smaller number on top, 1 liter on top, 2 liters on the bottom. I'm going to take 293, multiply it by 1, and divide it by 2. I'm going to get 146.5 or 147 Kelvin, which I then can check, and indeed is lower than 293. For my last one here, for this last law, a balloon initially occupies 12.4 liters at 1 ATM. What will be the volume at 0.8 ATM? So I have pressure, volume, and so my first pressure is 1 ATM. My first volume is 12.4 liters. My second pressure is 0.8 ATM. This one is nice because I don't have to deal with anything with Kelvin, but I look at this, my pressure is going down, which means my volume is going to go up because this is an indirect relationship, so I need to remember that. And so then I have 12.4 liters. I want my volume to go up, so I'm going to put my larger value on top. I'm going to put my smaller value on the bottom. And I'm going to do 12.4 times 1 divided by 0.8, and I get 15.5 liters, which is very nice because 15.5 liters is bigger than 12.4. So those are our first 3 basic types of gas law problems.